A pole-top capacitor is a device that's connected to a circuit to accept and store electrical charges. They're used to help overhead distribution feeder systems operate more efficiently and reliably. In this course, we'll begin by covering the basic theory and operating characteristics of overhead capacitors. We'll explain how to detect a problem in a capacitor's operation. And finally, we'll watch a crew in the field as they demonstrate how to safely replace a pole-top capacitor bank. But first, let's begin by reviewing the basic construction of a capacitor to see how it works. Then, we'll take a look at how a capacitor is used in an AC circuit to improve the efficiency of the current on the feeder. In this simplified illustration, we can see the basic parts of a capacitor. They consist of two parallel metallic plates separated by an insulating medium. In this case, air. In this example, one plate is connected to the line. The other is connected to the ground. Looking at a different view of the same capacitor, we can get a better idea of three characteristics that determine a capacitor's ability to store a charge. They are the size of the plates, how close the plates are together, and the material used to insulate the plates from each other. Increasing the area of the plates and moving the plates closer together increase the ability of a capacitor to store a charge. The type of insulating material used in the capacitor also affects its performance. Using a material with a higher insulating value will increase the ability of a capacitor to store a charge. Common materials used for insulation in a capacitor are kraft paper, linen paper, and oil. In the most basic capacitor, air is used as the insulating medium. The insulating value of other materials is usually compared to air. This comparison, or ratio, is called the dielectric constant of the insulating material and is expressed as the letter K. For instance, in our illustration, if air is used as the insulating medium, the value of K is 1. If the area of the plates and the spacing of the plates remains constant, but an insulating material is used that gives the capacitor twice the capacity it would have with air, then its dielectric value is 2. Now that we know how a capacitor works, let's take a look at what it can do. If the capacitor is connected to a DC circuit, current flows into the capacitor until the plate connected to the line is at line potential. Once at line potential, no further current flow will occur other than leakage from plate to plate through the insulation. The charge will remain until the capacitor is discharged, even if the capacitor is physically removed from the circuit. If the capacitor is connected to an AC circuit, the capacitor is constantly charging and discharging due to the cycling effect of alternating current. This charging and discharging causes current to flow into and out of the capacitor. When capacitors are added to a distribution feeder, the resulting current flow can be used to increase the efficiency of the feeder by changing the power factor. Power factor is the ratio of useful working power in kilowatts compared to the total power in kilovolt amperes supplied to the circuit. Total power in a circuit is made up of two components, working power and non-working power. Working power is the power available to do work. Non-working power is often referred to as reactive power. There are two types of reactive power, inductive and capacitive. Inductive power is the power in a circuit that is needed to magnetize motors, transformers, and similar equipment before any work can be done. Capacitive power refers to the power in a circuit that is needed to store a charge. The power in a circuit is the product of multiplying the voltage by the current. The relationship between working and non-working power is the same as the relationship between working and non-working current. Let's look at a sine curve of the AC voltage and current so we can see what the physical relationship is between working and non-working current. The phase relationship between the voltage and the working current is the same. Both have the same basic shape, and changes occur in perfect step or phase. However, AC circuits usually have equipment that must be magnetized. That part of the current that is used to establish the magnetic field lags the voltage by 90 degrees. When the voltage is at 90 degrees, the current phase curve is at 0. This current cycle is always 90 degrees behind its corresponding voltage. This current is inductive or non-working current. Let's go back to our illustration where the current and voltage are in phase. If capacitors are added to a circuit, part of the current is made to lead the voltage by 90 degrees. Capacitive current always leads the voltage by 90 degrees. Since capacitance has the opposite effect on current to inductance, the capacitive current cancels out a like amount of inductive current. The more the inductive current is canceled, the greater the improvement of the power factor. However, because the load conditions on the system are constantly changing, it is not practical to cancel 100% of the inductive current. To illustrate the relationship between working power, non-working power, and total power, let's use this illustration of a train. Here, the locomotive's power is available to pull directly on the train. In this case, the total power exerted by the locomotive is equal to the working power available to move the train. This is similar to a pure resistive circuit where the total power and working power are equal. Now, let's put the locomotive on a second track parallel to the first track and connect the locomotive to the cars with a cable so the locomotive can move the train. The locomotive has to pull harder than before to move the cars. Part of the total power the locomotive exerts is lost or non-working because the locomotive has to pull at an angle. The greater the angle that is formed between the straight pull and the cable connecting the locomotive to the cars, the greater the total power that the locomotive has to exert to provide the same working power to move the train. Now, if a power triangle is substituted for the train, we can see that the same principle can be used to show the relationship between working and non-working power in an electrical circuit. To do this, let's begin by labeling the angles of the triangle so we can refer to each part clearly. Line AB represents the working power in kilowatts. Line BC represents the non-working inductive power expressed in kilovars. This is the power that has been used to magnetize equipment along the circuit to that point. Line AC represents the total power necessary to do a given job. Total power is an algebraic or vector combination of the working and non-working power components. The formula for finding the value of the total power can be found in your textbook. Total power is measured in kilovolt amperes. When we give each line a numerical value, the power factor can be determined by the ratio between working power and the total power value. If the value for the working power is 100 kilowatts, and the value for the total power is 125 kilovolt amperes, the power factor can be found by dividing 125 into 100. The answer is 0.80, or a power factor of 80%. If there's an excess of capacitive power beyond what is needed to cancel out the inductive power, this will also affect the power factor. It can be expressed in a power triangle that forms on the other side of the line AB. Capacitors are normally added to a system in two different ways. One way is as a fixed capacitor. The other as switched capacitors. Capacitors that are connected to the system so that they are always online are called fixed capacitors. Capacitors that can be added to the system when needed are called switched capacitors. Switched capacitors are used to compensate for variations in load current. Well, we've just seen how capacitors can be used to improve the efficiency of a distribution feeder. We looked at the basic parts of a capacitor: two parallel metallic plates separated by an insulating medium. And we discussed the three characteristics that determine a capacitor's ability to store a charge: size, closeness of the plates, and insulating medium. We also discussed power factor, which is the ratio of useful working power in kilowatts compared to the total power in kilovolt amperes supplied to the circuit. In the next part of the program, we'll look at the basic parts of a capacitor bank. We'll also see how to make a visual inspection of a capacitor bank to identify common problems that can occur. In the last part of the program, we discussed the basic operating theory and characteristics of a capacitor. In this segment, we'll take a closer look at the parts that make up a capacitor bank, and we'll look at how to identify and safely troubleshoot them in the field when problems do occur. Before we get into troubleshooting, let's first take a look at a pull-top capacitor bank in the field and discuss some of the common pieces of equipment you'll see. On the distribution system, individual capacitor units are often mounted in multiples on a common bracket to form a capacitor bank. In this part of the program, we'll take a look at the parts of a typical capacitor bank and how it's connected in a Y system. And we'll see how a visual inspection of a capacitor bank can be helpful in locating some of the problems that can develop in a capacitor bank. The capacitors that are used on your system may appear different or may be connected to the system in a different way than the ones seen in this program. The equipment and procedures shown here are intended to be used as examples only. You should always become familiar with your company's specific equipment and procedures before any work is done. Let's look at the main parts of a typical capacitor bank. Capacitor banks have two parts in common: the individual capacitor units and the frame. On this capacitor bank, you can see the protective devices such as fused cutouts. We'll be looking more closely at those devices in just a few minutes. For now though, let's begin by looking at the capacitor units themselves. This is a single-phase capacitor unit. It has a tank and a bushing that will be connected to the phase, and either a lug or a second bushing that will be connected to ground. If we turn this capacitor tank around, we can see the inside of the unit through a cutaway. Instead of two flat plates separated by a flat thickness of insulation, we see a surface that looks like it's corrugated. Each of these corrugations, or cells, is a capacitor. Each has two plates separated by insulation that is rolled up. The individual capacitor cells are connected together at the top so that the value of the whole capacitor unit equals the sum of all the cells. At the top of the cells, each set of plates is connected to the bushing, and the other side is connected to the grounding lug. The other internal parts include bleeder resistors that connect the two sets of plates together inside the tank. The resistors are safety features that are designed to bleed off the charge on the plates. The charge should go to 50 volts or less after the capacitor unit has been electrically isolated for 5 minutes. While this is designed to reduce the shock hazard to personnel working around capacitors, you should always assume that a capacitor bank is fully charged until it is grounded or shorted. In a capacitor bank of single-phase units, one or more of the units for each phase may be connected together to get the total value of capacitance needed. In this case, the capacitor bank has three individual single-phase units. One unit is connected to each phase. The frame of each capacitor bank is made up of metal structural members and is mounted directly onto the utility pole. The frame allows individual capacitor units to be mounted to form the capacitor bank. It is also used to mount other equipment, such as switches, to the capacitor bank. The ground sides of the capacitor units are connected to the frame, which in turn is connected to the pole ground. For safety, the ground should always be connected before the capacitor bank is energized. Many capacitor banks, like this one, are switched banks, designed to be turned off and on rather than be online all the time. This capacitor bank uses a control mechanism located in a box lower on the pole to automatically switch the capacitor bank by opening and closing oil switches. The control mechanism is powered from a source of secondary power. The control mechanism can be preset to open and close the circuit to the capacitors during specific times of the day. It can also be set to operate on specific days of the week. For instance, this capacitor bank will remain offline during weekends because heavy three-phase motors used in this area are not expected to be operating. The control mechanism is connected to oil switches through a control cable. The oil switches are mounted on the frame of the capacitor bank. A jumper from each phase is connected to one side of an oil switch, and the load side is connected to the capacitor bank with another jumper. As we mentioned earlier, some of the protective devices used on a capacitor bank include fused cutouts and lightning arresters. The fused cutouts installed on this capacitor bank act as both switching equipment and protective equipment. A fused cutout is installed between the feeder and the oil switch. The fuses in the cutouts function mainly to provide protection for the feeder. If a fault were to develop on one phase of the capacitor bank, the affected fuse would blow, opening the cutout and isolating the fault. If this capacitor bank had no control mechanism or oil switches, opening and closing the fuse cutouts would be the only way to energize or de-energize the bank. In that case, when the fused cutouts were closed, the capacitor bank would be a fixed bank. Because there is a danger of arcing, it is important to follow your company's guidelines when opening and closing the cutouts on a fixed capacitor bank. Lightning arresters are another device often mounted on a capacitor bank to act as a protective device. The arresters are designed to prevent damage to the capacitors in case of voltage surges. Now that we've identified some of the basic parts of a capacitor bank, we'll follow along as a line worker makes a visual inspection of a three-phase capacitor bank. It's important to realize that special care must be taken when working around capacitors. Even when the circuit is de-energized, the capacitors may still hold a charge. Although the bleeder resistors are designed to reduce any stored charge to 50 volts or less within 5 minutes, it is possible under some conditions that the resistors will not do their job. Capacitors should always be treated as fully charged until they've been de-energized, shorted, and grounded. A report was called in earlier that some of the equipment on this pole was not working correctly. A line worker was dispatched to the job site to inspect the capacitor bank.
When he arrives at the job site, the line worker first checks the control for the capacitor. He finds that the bank is not functioning properly. The line worker next opens the fused cutouts.
After the bank is de-energized, the line worker performs an inspection of the bank. In this inspection, he checks for any sign of discoloration or corrosion that would indicate that the units have overheated or have been damaged. In addition, he also inspects the tanks of each unit for obvious signs that they're defective. For instance, he looks for any signs of an oil leak or for sides that are bulging out on any of the tanks. Then the line worker checks the fused cutouts and oil switches. If one phase had been open while the other two remain closed, it might indicate an internal problem with one of the capacitor units. Performing a visual inspection after de-energizing the bank allows time for the capacitors to bleed off the stored charge. The bank can then be grounded using your approved company method. If there are no visual signs of damage, the lineman then uses a C meter or capacitance meter to check each capacitor. After comparing the C meter reading to a range chart, one capacitor was found to have been damaged.
The line worker leaves the capacitor bank disconnected for the changeout crew.
The line worker notifies the proper authorities that the capacitor bank has been damaged and is inoperable. Well, in this part of the program, we took a look at the parts that make up a pole-top capacitor in detail, and we discussed how to troubleshoot problems when they occur. Take some time to review the material in your workbook, and if you have any questions about the material covered, be sure to ask your instructor. In the next part of the program, we'll join a changeout crew in the field as they investigate the troubleshooter's report and replace the malfunctioning capacitor bank.